As an application of our discussion on modifiers and convolutions, we prove the following fundamental lemma of calculus of variations. So suppose we have a locally integrable function u, wherein the integral of u times any test function is 0, then this would imply that u must be 0 almost everywhere in the domain omega. Well, in connection to the uniqueness of weak derivatives, u would represent the difference of, let's say, two weak derivatives. Then this fundamental lemma of calculus of variations would imply that the difference would be 0 almost everywhere, hence the uniqueness of the derivative almost everywhere. So to look at the proof, let us start first with a compact subset of Rn, or of omega. And if x is in K, let us define phi sub k of x, phi sub k raised to x. So consider here x as a parameter to be this difference. This is a function of y, and y is in omega. Then we know that the support of phi kx would be a subset of, so the modifier phi sub k will be translated x 1 over k. And take note that our construction of the modifier is radially symmetric. Take note that phi depends only on the norm of x. Okay, and using this, take note that since x is in K, so this would be a subset of K plus this closed ball. And this is a subset of omega, since K is compactly contained in omega, and if we take a K large enough, so that this set would be small, and we are sure that this sum is in the open set omega. Therefore, this translated modifier is also a test function. And according to our assumption here, if we take phi to be this phi sub k to the x, this would be 0. And take note that if we extend, let's say, phi sub k to be 0 outside omega, then this is equal to this integral x minus y dy. And this is the convolution of u and phi sub k of x. And of course, we know that this is the same as this one, according to the commutativity of the convolution. Now, we have established in the previous discussions that this converges to u in L1k. Take note that this is true in all Rn, hence true in the compact set K. So let us emphasize here that we need to extend u, and this function by phi k x by 0 outside omega, so that the integral can be taken over all Rn, and you can write this as a convolution. A strong convergence in L1 implies the existence of a subsequence such that this subsequence of convolutions converges to the limit for almost every x in omega. However, we know that this is equal to 0 according to this part here. Hence, u must be 0 almost everywhere in K. And then we apply this to the to a countable compact sets in an exhaustion of your open set omega, so that you can also conclude, in fact, the convergence, or u being 0 almost everywhere in each compact set of this sequence. And since this is a countable sequence, and you apply, let's say, the subadditivity of the Lebesgue measure, and you will get that u is still 0 almost everywhere in omega. And that's the proof of the fundamental lemma of calculus of variations. So to close the discussion on this section, let us present the following density theorem for the Sobolev spaces. And this is due to Meyers-Serrin. And it is based on the paper having the title H equals W. And what does this theorem tells us? So if you have an open set omega in Rn, a positive integer k, and a finite p, then the set of C-infinity functions in the Sobolev space WKP is dense in the Sobolev space WKP. And why does they call it? Why does the variable h appear here? Well, in other references, if we define, let's say, the other Sobolev space HKP omega to be the closure of course, the closure is taken with respect to the WKP norm. Then this is the same as WKP. So that's why it is called H equals a W, because this is a subset of WKP. You can take the closure And in fact, in this case, the closure is the same as the WKP space. So let us defer the proof of this theorem at the end of this lecture. And let us discuss some application of this theorem. And this will illustrate the importance or the advantage of having dense subsets with more properties. So take note here that functions in this space are infinitely differentiable. And they are, moreover, they are continuous. So to illustrate, let us consider, let's say, the product rule for Sobolev functions. So we know that the product rule holds for strong derivatives or the classical derivatives. It is also true for Sobolev functions under, of course, appropriate conditions. So let us take P and Q that are dual to each other. In other words, the sum to reciprocals are equal to 1. If I have two functions, let's say f in W1P and g in W1Q, then the product is in W11 and the weak derivatives satisfies the product rule, which is the same as the product rule in the case of the classical derivatives, I from 1 to n. So to look at how Meyers-Serrin can be applied here, but before doing that, you can easily check by a Holder's inequality that Fg and then the terms on the right hand side are all in L1. Hence, they are also locally integrable. So without loss of generality, let us assume that P is finite. Otherwise, you interchange the rules of P and Q. So if this is the case, according to Meyers-Serrin theorem, I can find a sequence, call this f sub j, WKP. Let us write first in C infinity, intersection WKP, such that f sub j tends to, so k is equal to 1 in this case. So this should be W1, such that f sub j converges to f in W1P omega. That is, f sub j tends to f, and also the weak derivatives dIFJ tends to DIF in LP. Of course, here for all I, from 1 to n. And this is according to the definition of the norm in the Sobolev space W1P. Okay. Now we would like to prove this identity here in the weak sense. So the derivatives are taken in the weak sense. So let's start with a test function. Then, as a phi and f sub j belong to C infinity by the usual product rule for functions. So the product rule, derivative of the product is equal to this quantity. So di phi f plus phi di f. Okay. Now let us investigate this integral here. Sub j g dx. Okay, so the idea here is to pass the derivative here. And but of course we cannot do that because g is not smooth. What we do is to rewrite this in the following way. So we separate g from the functions that are smooth. Okay, this term is precisely this term. So from that we have the following. This is the derivative of the product of phi and fj minus phi, then the ith derivative of f. Applying the definition of the weak derivative, and since we know that g is weakly differentiable, so this would be the first integral. The second integral will be the same. However, write it in this way by commutativity and associativity of the product of numbers, of course. And this is the same as, okay, now we have a common factor phi. So I should factor that one. And we have the following. This is, let us start with this term. Plus, and then this one. After factoring phi, you have f sub j. I'm missing a subscript j. F sub j dig. Okay. Now, as in the case of the weak derivative, if you have this term here, this term, if you pass, let's say, j to infinity, apply Holder's inequality and this limit here. And we did that as before, you would get the following identity. X, phi, DIFG plus F sub j, or F, DIG. And this is true for any test function phi. So therefore, this must be the weak derivative of the product. And the proof is now complete. Okay, so that's the product rule for Sobolev functions. So the idea is to choose one among P and Q to be finite, and we choose P without loss of generality. And why is that? Because that is what is needed in the Meyers-Serrin theorem, specifically this condition here. And then you consider, we take a sequence of smooth functions that will converge to F. So that is the crucial part of the proof. And of course, applying the usual product rule. This argument here is sometimes called a density or even an approximation argument. So in the exercises, you're asked to prove also the chain rule for Sobolev functions under appropriate conditions. You're also asked to prove the weak differentiability of the max and min functions. Okay, so for this last part, let us consider the proof of Meyers-Serrin theorem. So I decided to present the proof since it has, it has some delicate arguments, and the ideas are good. So we will do this in 3 steps. So proof of Meyers-Serrin theorem. So the first step is to construct a partition of unity. And you will see why this is called the partition of unity. For large M greater than 0, let us consider an exhaustion of the open set, omega. So J here would be 1, 2, and so on. So we have a countable sequence of compact sets of omega. So in this case, one can choose, let's say, according to the previous discussions on exhaustions, you can take this compact set. So take all points in omega having distance at least 1 over j plus m. M here is to guarantee that this is a non-empty set. And you take, of course, this can be unbounded. So you take the intersection with this compact ball. And for this, let us define U sub j to be the interior. And let's say this is, of course, for j equal to 1, and so on. So according to this construction, since you have an exhaustion, the compact set k tilde j will be a subset of, well, it's not a uj, but a uj plus 1. So from this exhaustion and collection of open sets U sub j, we define another increasing sequence of compact sets. And let's say k sub 0 to be the closure of U sub 2. And v sub 0 to be U sub 3. So this is illustrated in this way. Take note that since the k sub j's are increasing, then these are also increasing. The open sets, so this is an increasing sequence of open sets. Okay, so k naught is defined in that way, and v naught is defined this way. For j greater than or equal to 1, okay, so what we do is we take the closure of uj plus 1 and then subtract uj plus 1 for the closure of uj plus 2 and subtract uj plus 1. Since the u's are open, this case of j is what? A compact set minus an open set, so that would be still a compact set. On the other hand, we define v sub j to be uj plus 3, which is open, minus the compact set uj bar. So this is an open set. So these are the v sub j's are open sets, while the k sub j's are compact sets. Okay, based on this construction, we have the compact set k sub j is contained in v sub j. So looking at these figures, by construction, we have this for every j. Let's start the index with 0. And by this construction, we also know that omega is the union of the k sub j's. And this is also the union of the v sub j's. Since all of these are obtained from the exhaustion. the K tilde sub j's. Take note that if you have an exhaustron, then you have this property as well. Now, for each j, there exists a plateau function, h sub j, compact, infinitely differentiable, and compactly supported in V sub j. The values are between 0 to 1, and if I restrict this to the compact set K sub j, it is equal to 1. An example of this would be the following. You first consider the indicator function of K sub j. You add a small ball to this compact set. You modify this, or take the convolution with this modifier, phi sub n, and you define this function. According to our discussion, this is since the characteristic function of the compact set is locally integrable, and this is in C0 infinity Rn. Take note that the support of this convolution is a subset of the support of phi sub n plus the support of your set involved in the indicator function. Okay. Plus some. Okay. Is that enough? Let's go back to what we know. Going back to our discussion. So you have this. Okay. So we need to replace this by a closed ball. And we know that so also take the closure of this one. We know that this is equal to K sub j plus, of course, you can just add the radius. And this is a subset of B sub j, since K sub j is compact, B sub j is open, and a K sub j is contained in B sub j. So the idea here is that if you have a compact set K sub j contained in some open set, V sub j, what you do is, if you add a small width to this compact set, this width here would be this radius 1 over n plus epsilon. So we are guaranteed, if we choose n large and epsilon small. So we are guaranteed that this neighborhood of the compact set K sub j is still in the open set of V sub j. Okay, so as an illustration of these plateau functions, take note here they must be 1 on the compact set K sub j's. So in this case, H naught would be 1 on K naught. So this is K naught. So this is K naught, first set. So H naught must be 1 there. And since it has a compact support, it will decay to 0. Or it outside some set, outside some compact set, this figure, outside this interval, H naught would be 0. So you can think of this as some sort of a side view for what we have discussed. Okay, so for this one, so you will have a plateau function in this case. For instance, something like this. It should be 1 here. So you look at the side view, for instance. So in this case, H1 would be identically 1 on K1. So here K1 consists of 2 compact sets, and it is 1 on those intervals, at least in this figure. And also for H sub 2, and there's a typo here. This should be K sub 2, K sub 1, and K sub 2. Okay, so the sum of these functions is not necessarily 1, because if you take the sum, for instance, of these 2 functions here, you will obtain a certain bump. So to compensate that one, let us define psi sub j to be H sub j divided by the sum. And it's clear that this is in this space. Since the support of H sub j is contained in V sub j. I would like to emphasize here that this is not an infinite sum in reality. This would be a finite sum at each point, since x will be in V sub j for at most 3 indices j. And why is that? Because here V sub j consists of only this set, the 3 indices corresponding to j plus 1, j plus 2, and j plus 3 for the open sets U. Okay. X in U sub j. Okay, and with this, we can see also that since phi sub j has been normalized, is non-negative, and the value will now be at most 1. And in fact, the sum of the size of j's is also equal to 1. And this is what we call the partition of unity with respect to the exhaustion of the open set. Okay, so that's the first part. For the second step, we now do a local approximation. So instead of considering on the whole domain omega, we consider on the open set B sub j's. So first, let us take a Sobolev function in WKP. We cut off this function by multiplying phi sub j, and the product rule shows us that this product of C0 infinity function with f is also a Sobolev function in WKP. And we set f sub j to be 0 outside omega. So on the complement, we define f sub j to be 0. Then, well, obviously, f sub j will now be in WKP Rn. Now, for a multi-index with length at most k, you can apply the Lebesgue-dominated convergence theorem to put the derivative of the convolution into the modifier. And also to the function f sub j. And we know that this tends to the weak derivative in, of course, in LP as k or as I tends to infinity. And we have shown this last time. And let us write this convolution here as G sub I j. Then G sub I j using the formula for the support for the convolution. You have this for large enough. Index I. So that the support of okay, so let us write it down. So that the support of Gij is a subset of the support of f sub j plus this ball, and this is contained in the support of f sub j. But since the support of psi sub j is compact in v sub j, this would be a subset of v sub j. So given epsilon greater than 0, there exists, let's say, this I sub 0 large enough such that f sub j minus gi not j, however the norm is taken in the whole space Rn, let's say this is less than epsilon, okay, plus some convergence series. So let's take the geometric series with the ratio 2, 1/2. And for simplicity, let us define this as g sub j. And now for the final step, again, I just repeat the process here. The local approximation here is by cutting off your function so that the support of your function f sub j would be a subset of b sub j. So we have localized the support. Global approximation means that we want to extend this to the whole domain omega. So we glue the functions g, meaning let g be the sum of the g sub j's. This is obviously in C infinity. And take note that the sum of the f sub j's and we should start at 0 with the definition of the f sub j's. This is psi sub j's times f, but since this is a partition of unity, then this is basically f in omega. Now for n large enough, we can say that, let's say, G would be a finite sum, and F is also a finite sum. On or in, let's say V sub k. This n here depends on n sub k. It depends on k. So since this is an open set that is contained in a compact set. Thus, if we apply the triangle inequality, we should use a different index. Let's say V sub m, not to be confused with the order of differentiability in the Sobolev space. So V sub m we just apply the triangle inequality. And of course, this is still larger if we take the norm in the whole space Rn. And applying this using the geometric series, it is not hard to see that this is less than epsilon over 2. Now, note that if I consider the sequence of these restrictions m from 1 to infinity, this is increasing and converges pointwise to the whole function f minus g on the domain. Since here Vm increases and converges to the open set omega. So we have an increasing sequence of functions that converges pointwise to this difference. If we apply the monotone convergence theorem, okay, we do this also for all for the weak derivatives. If we apply the monotone convergence theorem, and the limit as m goes to infinity of this, let's say, WKP VM norm. Okay, let us raise that to P for simplicity. This is the sum, according to the definition, of the Sobolev norm. We can take the integral over all, let's say, omega f minus g. But of course, you need to take the restriction. So this is d alpha f minus g restricted to Vm. Dx raised to the power p. So if we apply the monotone convergence theorem, this is equal to this integral. And since this this is always less than epsilon over 2, so this is less than or equal to epsilon over 2, hence less than epsilon. And take note, this is nothing but the Sobolev norm of the difference. And this also implies that G is in WKP omega. Okay. So this is less than epsilon. So let us include it, this part here. And that's the end of the proof. because we have found, so going back to the second step, given a Sobolev function, we have determined a C infinity function in omega that is also in WKP that is sufficiently close with the given Sobolev function f, in the sense that the distance is less than the given epsilon, with the given epsilon. And that's the proof of the Meyers-Serrin theorem.